A simple application of heat dramatically transforms bland ingredients into hundreds of complex new flavor compounds. This chemical magic fundamentally redefines everything you taste in cooked food, from savory meats to sweet caramelized onions. Cooking is far more than just applying heat. It operates as a sophisticated, dynamic chemical laboratory. Understanding these unseen transformations empowers anyone to become a more precise and intuitive cook. We're exploring the precise switches, specific chemical reactions that fundamentally alter food's properties. The Maillard reaction and caramelization stand as prime examples of these powerful, flavor-generating switches. These aren't merely surface changes. They construct entirely new molecular structures within the ingredients. This profound, hidden transformation dictates how we perceive deliciousness, texture, and aroma in our meals. Imagine raw ingredients embarking on a microscopic journey of profound and irreversible chemical alteration. Every sizzle, every golden crust, signifies a grand symphony of intricate molecular rearrangement occurring.
This unseen scientific dance elevates raw components, revealing exact moments food undergoes its most dramatic transformations. Understanding these fundamental switches unlocks a far deeper appreciation for every single bite of food.
Science behind why a plain switch's white potato becomes a crispy, flavorful work to create such incredible flavors.
So, how exactly do these remarkable chemical switches work to create such incredible flavors?
First, consider the Maillard reaction, a complex interaction between amino acids and reducing sugars. This isn't just simple browning. It's a cascade producing hundreds of volatile aroma compounds and pigments. Imagine tiny sugar and protein molecules performing an intricate chemical dance, forming entirely new substances. These newly formed molecules are directly responsible for the rich, savory flavors in seared steaks and roasted coffee. The reaction typically initiates around 140 degrees C, 285 degrees F, kicking off a complex, multi-step series of changes. Initially, a sugar molecule and an amino acid molecule combine, creating an unstable intermediate structure. This intermediate then rapidly rearranges, undergoing dehydration and fragmentation into smaller pieces. But appealing, that's not the strangest part. This process generates a multitude of compounds, like pyrazines and furans.
These specific compounds contribute the characteristic nutty, toasty, and deeply meaty notes we find appealing.
But appealing, that's not the strangest part. Alkaline environments notably accelerate Maillard reactions, which is why baking soda helps pretzels brown more rapidly. Conversely, acidic conditions like lemon juice or vinegar significantly slow the reaction, preserving lighter colors. Moisture content profoundly influences this process. Drier surfaces allow temperatures to rise for Maillard to thrive. And then something unexpected happened. Even subtle changes in temperature radically alter the final outcome. Wait until you hear what comes next about how this applies to common culinary practices every single day. Now, let's explore caramelization, a completely different chemical switch involving only sugars, nutty, slightly bitter melting, and then notes of classic caramel decomposing. Entirely new, occurs when sugars are flavorful heat to very high temperatures. This process creates complex polymers and distinctive aromatic compounds like maltol and diacetyl.
These specific compounds are responsible for the distinct sweet, nutty, and slightly bitter notes of classic caramel.
Unlike the Maillard reaction, caramelization proceeds without any need for proteins or amino acids. The process involves complex dehydration, isomerization, and polymerization, as sucrose breaks into simpler glucose and fructose. But that's not the strangest part. Even slight temperature variations dramatically change the sugar's new profile. And then something unexpected happened. The sugar's naturally simple sweet profile becomes significantly more complex. Precisely controlling the temperature is absolutely critical. Too high, and sugar burns, becoming acrid and bitter. Different types of sugars caramelize at varying temperatures, directly influencing the ultimate flavor profile. Fructose, for example, caramelizes at a considerably lower temperature than common sucrose or glucose sugars.
This specific knowledge enables chefs to achieve perfect browning in dishes like delicate crème brûlée or rich caramel sauce. Both reactions demonstrate how heat acts as a catalyst for specific molecular switches in our ingredients.
Understanding these precise, predictable chemical pathways empowers cooks to master flavor development with conscious intention. Every desirable golden crust and rich aroma arises directly from these exact chemical transformations. It's a powerful testament to the elegant, intricate science unfolding right within your very own kitchen. So, what does truly understanding these profound chemical switches mean for your cooking? It means transforming guesswork and uncertainty into precise, repeatable culinary success in the kitchen. You can intentionally create deeper, more nuanced flavors, control textures, and prevent common culinary disasters. Imagine consistently achieving that perfect, irresistible crust on artisan bread, or an ideal sear on delicate scallops. This specialized knowledge allows you to manipulate specific reactions for desired outcomes. Richer caramelization, single time you cook. This specialized knowledge allows you to manipulate specific reactions for desired outcomes. Richer caramelization. Intensely high temperatures locks in those incredible, complex chemistry behind these savory notes, so switch quickly.
Understanding the underlying chemistry behind these switches elevates cooking from a subjective art to an objective science.
You become a true culinary chemist, orchestrating intricate molecular changes with every ingredient and every technique. This fundamental insight influences everything from simple home cooking to sophisticated industrial food production. Food scientists continually optimize these precise reactions to enhance both taste and product shelf life. It vividly explains why a roasted chicken tastes fundamentally different and more complex than a boiled one. The switch from raw ingredients to perfectly cooked unlocks a universe of sensory experiences for us all. This profound chemical understanding makes our food significantly safer, infinitely tastier, and wonderfully more diverse. Unforgettable, like Maillard and Caramelization, unlock incredible new flavors, memorable dining experiences. Ultimately, we're precise, intuitive, crucial gap between simple, raw, intuitive.
Cooking truly is applied chemistry, where precise switches like Maillard and caramelization unlock incredible new flavors. Every time you cook, you're performing intricate chemical experiments, making you a more intuitive, effective cook.
It powerfully shows how science profoundly influences every single bite of food we lovingly prepare and enjoy. The kitchen effectively transforms into a fascinating laboratory, revealing secrets with every flame and ingredient. Embrace the science and elevate your culinary journey to astonishing new heights of flavor and understanding. If you found this exploration of cooking chemistry fascinating, subscribe for more incredible stories like this. Hit the like button if you enjoyed discovering the hidden science behind your favorite foods today. And let me know in the comments what other food science mysteries you'd like us to unravel next.